So this is on partial pressures, and let me see. Normally you're here. So gas laws and partial pressures, that's what we're focusing on. Before we talk about the gas laws and we get onto all those calculations, we're going to talk about these Maxwell-Boltzmann distribution graphs. So what they do is they show the particle speed, how it's distributed. So this particle speeds can go from like 0 to basically 1,500 meters per second. They're somewhere, all the particles in a gas are somewhere in between there. The x-axis will always be the speed or velocity of the particles. And then your y-axis will be like how frequently we find particles at that speed. Sometimes they can be a fraction on the y-axis, or they can be just a number. So like 0.00, a probability. And then the area under the curve is constant. So like no matter what, if I have a slow or a fast, hot or cold gas, I'm gonna have the same area underneath. I'm not gonna have necessarily the same shape, but if I were to take the area of this and maybe of another graph that's showing the distribution, it would be the same area, okay? Because it represents 100% of the particles. The way you might read one of these graphs is like you pick a certain speed or velocity, and you would just go up and you would see like, okay, the amount of particles going 500 meters per second in this case would be like 0.0012. Now, if you remember from our previous notes, gas particles that are hotter or at higher temperatures, they're going to be moving faster because they have more average kinetic energy, right? So the faster they go, the more kinetic energy they have, which is the temperature. So this, I have basically about like 500, most of my particles are 500 meters or less. We're not necessarily over here on this range of the higher velocity. So I can basically tell that this is probably at a colder temperature. Either that or I'm at like a heavier molecule. So they're kind of moving at a slower pace. Okay. All right. So next, does anyone need more time with this, or you guys are okay? I put this on Google Classroom as well, so just in case. So now let's compare. We're comparing two different gases at different temperatures, different masses. So if we're talking about temperature, if the temperature increases, there's going to be a greater number of particles with higher speeds. So we're going to have some at 0, just because when they hit each other, that temporary is a 0, or when they hit something, it's a 0 velocity because they're changing direction. And then what ends up happening is it flattens out. Now we still have, oh shoot, excuse me guys. Okay, so we still have a few particles that are going to be slow, again, because they're changing direction or just any real reason. But most of them are going to be on this side where they're going faster because we have an increased temperature, increased kinetic energy, which means the increased speed. Again, the area that was under our cold gas is now the same area. So if we took this right here, spread it out, we would have the same amount of area here. It's just that we flatten it out and we extend it, okay? So if you were comparing gases, this is what you would see. Like, for example, if you had a question of this is a gas that we were given, what happens if we heat it up? Then you would have to draw something like that, okay? Same thing happens with masses. So if we were comparing a heavy gas to a lighter gas, we would see about the same type of graph. And the reason is, remember, heavier gases or things that are more massive are going to be slower. They have the same kinetic energy, remember, because kinetic energy is mass times velocity. So their mass makes up for the speed, but they do move at slower speeds. So our bigger gas particles will move slower, and the lighter gas particles are going to move faster. So in this case, this would be like a heavier gas, this would be a lighter gas. Does anyone need more time, or you guys are okay? You good? Okay. So look at this question here. This is just a question that you might see on the AP exam. It says the graph above represents a particle speed distribution for a gas at a certain temperature. It doesn't tell you the temperature, it just tells you this is our graph of a gas. Which of the following graphs represent the speed distribution of a heavier gas at the same temperature? So which one, A, B, C, or D, the red arrow is the heavier gas, represents the correct graph that we would see? If you look at it and then just type it into the chat what you think, A, B, C, or D. Which one would be the heavier graph for the gas? And remember what we just talked about in the previous one, okay? Yes, a lot of you are correct. So if you remember, this kind of is a fast gas. The reason is we have it more spread out and we have more particles in this range over here, okay? So if this would be wrong because this is showing us an even faster gas than this. So that means that it would be lighter, if anything. So this would be wrong. This one, which a lot of you guys picked B, is correct because we have a heavier gas is going to be slower because it's heavier. It has to move more mass. So this is the correct graph for a heavier one. This would be wrong too, C. The reason is because it doesn't have the same area underneath the curve, and we need the same area, okay? And then over here, this would be wrong because what this is saying is we have another faster gas because we have some particles over here. So we flattened it out even more. So this would be wrong. So this is the correct one because it shows that more of the particles are in the slower range, which we should see because we have a heavier gas. Okay, so now partial pressures. This is basically saying whenever you have a mixture of gases, doesn't matter what the mixture is, The partial pressure is the pressure exerted by each gas. So let's say we had a mixture of hydrogen, helium, nitrogen, oxygen. Each type of gas, or each hydrogen, helium, nitrogen, oxygen, would have its own pressure. Ideally, if it's an ideal gas, which most times they are, they're going to behave the same. It doesn't matter if it's oxygen, gas, nitrogen, whatever. They're going to behave similarly. And what we would do to get the total pressure is we would add up all the partial pressures. So say I had my oxygen, nitrogen, helium, hydrogen, or whatever I said. This would be the pressure of oxygen, the pressure of helium, the pressure of nitrogen, the pressure of hydrogen. We would add them all up together, and then we would get our total pressure. So that one's not too bad. Those are actually some of the easier problems, because sometimes I'll be like, oh, if you have a pressure of this and you mixed it with this and now you have a total pressure, what was the pressure of this gas or something like that? And you would just, input your information and then solve for whatever it was asking for. Okay. Now we're going to talk about mole fraction. So mole fraction is the ratio of moles of one gas in a mixture. Basically, it's almost like the percentage, but you don't multiply by 100. You just get the point, the decimal, okay? A lot of times what they like to do is they like to, let Alicia back in. A lot of times what they like to do is they like to give you a representation, a particle representation like this, and they ask you to figure out the mole fraction. So you can do mole fraction by counting molecules, and you could just make them either molecules or moles. It doesn't matter. It's going to give you the same ratio. And in this case, if we were to look at the red ones, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 5 of the blue, and in total there's 15. So to figure out the mole ratio, we get the amount that we want. Moles, it could be molecules if you have that, over the total. So in this case, we'd have 10 of the red over the 15. So our mole ratio would be 0.67. And that's how you do mole fraction. This is probably one of the easier ones to do, just because it's, just the part divided by the whole, or total. Okay. Now, partial pressure and mole fraction basically are equal to each other. So if you have the mole fraction, you can find the partial pressure, and if you have the total pressure. So like if we wanted to figure out what is the pressure of the red one, we know that the mole fraction in this case, if we go back, was 0.67. So all we would need is the total pressure. So let's say we were to do this and we would get whatever pressure was at a certain temperature. Let's say it was at, I don't know, 2.5 atmospheres. Then we would put 2.5 atmospheres, the total, times 0.67, which is the mole fraction for red. And that would give us our partial pressure for red. Okay, so in that case, if we had 2.5, we'd have 1.68 atmospheres. That would be the pressure for the red molecules or gas particles. And that's how you combine partial pressures and mole fractions. Does anyone have any questions so far about these? This is a really good formula to know. When you guys take the exam, they don't give you that many formulas, especially when it comes to gases. They're like, you can figure it out. Let me see specifically which ones they do give you. They give you, for gases, they give you ideal gas law. They give you, oh, they do give you this one. They give you this right here. The partial is equal to mole fraction times the total pressure. They give you the partial pressure one. And yeah, that's it. They don't give you anything else. That's all they give you is that. Okay. And they give you density, I believe. So that's all you get. So since this one's given, I guess you don't really have to memorize it because they give you this. But just know that the mole fraction is equal to the partial pressure. Okay. All right, so now we're gonna go into our many, many, many gas laws. There's like 5 of them. And there's tons of calculations that you can do. Since there are so many, we're gonna focus on 2. And these 2 will get you through almost every single problem that you could think of with gas laws, okay? So instead of me going through like Boyle's law and Charles' law and Gay-Lussac and all that stuff, we're just gonna focus on 2. I am gonna give you the other ones just so you know them, but you don't really have to memorize them. You don't really have to worry about them. So for the first one, it is Boyle's law. And the formula for Boyle's law is P1, pressure 1, times volume 1 is equal to pressure 2 times volume 2. If you were to look at a graph for Boyle's law, comparing it, this is since pressure and volume are inversely proportional. When one goes up, the other one goes down. Remember that this is the type of graph you should see. Okay. The next one is Charles's law. And this is, volume, not pressure. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. And if we were to look at the graph of this one, we would see this because they're directly proportional. So when one goes up, the other goes up. When one goes down, the other one goes down. Okay. The next one I have to double check because I always forget. Okay. So the next one is Gay-Lussac. And this is pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. And again, pressure and temperature are directly proportional. So when temperature goes up, pressure goes up. When temperature goes down, pressure goes down. So we would see the same type of graph as Charles. Okay, when one goes up, the other goes up. When one goes down, the other goes down. Now these are all whatever, they're fine and dandy or whatever. But the real ones that we really love and adore is combined gas law. Which combines all of these together. That's why it's called that. And it is pressure 1 times volume 1 over temperature 1 is equal to pressure 2. Like that. Pressure 2 times volume 2 over temperature 2. Okay, and I am going to put sparkles and glitter and stuff all over it because it's so important. This is the one, you can forget the other ones, remember this one. And then the next one we have is ideal gas law. We've discussed ideal gas law before. But with these two, and this is pressure times volume, is equal to moles times a gas constant times temperature. These two are your two that you just care about. The other ones, we don't really care about. The most thing we care about is maybe the graph, but that's about it. Okay. These are your real ones. So we're mainly going to use these two. And the reason is because if we don't have, like, for example, volume as one of the variables, then we can just use the ones that are pertaining to us. So I am going to do, I'm hoping all of you guys got that. I'm going to do some problems for you. And in these problems, I have here's my combined, here's my ideal, and then here's my value for R. These are some conversions for pressure that I have. So I'm going to use my combined gas law and my ideal and see which one I would need for these problems. So for the first one, it says the temperature inside my refrigerator is 4 degrees Celsius. So this gives me my initial temperature. The temperature in my kitchen is 22. This gives me my second temperature. Actually, you know what? I have to do it backwards because the balloon is in the kitchen. So this is my first temperature because the balloon's in the kitchen. And then I have my first volume. It wants to know what will happen if you put the balloon inside the refrigerator. So this is my second temperature. Okay. So what I would do is I have T2, T1, V2, and V1. This is what I want to find out, what the new volume is. So I would look up here to my combined gas law. And since it doesn't talk about pressure, my pressure is going to be constant, and I'm just going to ignore that. So the formula I'm going to use is going to be V1 over T1 is equal to V2 over T2. Now, my volume is in liters. Great, I love that. I don't like my temperature in degrees Celsius. They're never going to give, it's very rare that they'll give you Kelvin. They mostly will give you degrees Celsius. So you're going to have to convert. So for this, the way I convert is 4 degrees Celsius plus 273 equals 277 Kelvin. Here I'm going to have to convert for my first temperature. So I have 22 degrees Celsius plus 273 gives me 295. Then I would just plug in here and solve for V. So my initial volume is 3.5 liters. My initial temperature is 295. I don't know what my second volume is. That's what I want to figure out. And then my fridge volume, which I want to see what happens to the volume when I put it in the fridge, is 277. So I would solve for V by multiplying both sides by 277. This is kind of like an algebra problem where you solve for x, with V being your x. And when I do this, I get a second volume. So my volume is going to be 3.29. And actually, it would only be 1, but it's okay. 3.29 liters. Okay. And that's how you would do this first one. For the second one, it is asking the weather balloon has a volume at 35 liters and at sea level. The pressure is 1 atmosphere. Again, I love liters for volume, love atmosphere for pressure. After the balloon is released, it rises where the air pressure is 0.75. Again, atmosphere is great. I love that I have atmospheres. And I want to know what the new volume is. So here's my V1, here's my P1, this is my P2, and I want to figure out V2. So I use my formula. Temperature is not even a factor here, so it's going to be a constant, so I ignore temperature. And I would have this, P1 times V1 equals P2 times V2. Okay, and I would just plug in my information. So my first pressure is 1 atmosphere. My first volume is 35 liters. My second pressure is 0.75 liters. And I'm solving for my second volume. So I would solve for V2, and I would do that by dividing both sides by 0.75 liters. Oh, this is not supposed to be liter. I'm like, wait a minute, we're solving for volume. What is this liters? That should have been atmospheres. My bad, guys. Okay, so our V2 would end up being 46.67 liters. And if I wanted to do this significant figure, I have 2 significant figures in each. So this would be 47 liters if we were finding significant figure. Okay. Any questions so far? Okay, I'm going to continue. If the sun heats my car from a temperature of 20 degrees Celsius to a temperature of 55 degrees Celsius, what will be the pressure inside the car? Assume that the pressure is 570 millimeters of mercury. So all of these have to be converted, but I have temperature and 1, temperature 2, and then pressure 1. And I'm solving for pressure 2. So my formula would be P1 over T1 equals P2 over T2. To convert from millimeters of mercury to atmospheres, you would divide by 760. So 1 atmosphere equals 760 millimeters of mercury. And then my temperatures I would need to convert. So my initial temperature is 20 degrees Celsius plus 273 gives me 293. My second temperature is 55 degrees Celsius plus 273, I believe 328. Yes. Yes. Yeah. Okay. And then this one I would have to convert. So 570 divided by 760 gives me 0.75. Oh, can you get it? So here my pressure would be 0.75 atmospheres. So then I would plug it in here and solve for P2. 0.75 over 293. And again, I would multiply both sides by 328 to get rid of it. And I would have a pressure of 0.84 atmospheres, which makes sense because directly proportional, if our temperature goes up, our pressure should go up. Okay. All right, for the next one, we have a gas sample that has a volume of 252 milliliters. We have 23 degrees Celsius, so this is our volume. This is our temperature, this is our pressure. And it wants to know what's the new volume. So all of these are volume 1, temperature 1, pressure 1. And what's our new volume? If we are at 0 degrees Celsius and then 760. 760, again, 1 atmosphere equals 760. So if you ever see 760 mmHg, it's 1 atmosphere. Okay? And then here's our second pressure. So we would use the combined gas law. We'd have V1 times P1 over T1 is equal to V2 times P2 over T2. The only thing is I have to convert my temperatures, and with your volume, you could convert it to liters if you would want. I would get in the habit of doing that. You would just divide by 1,000. So anytime you have milliliters, divide by 1,000 to get liters. So that would be 0.252. So for my initial volume, I would have 0.252 liters. My initial pressure would be 1.5 atmospheres. And then for my temperature, it'd be 23 plus 273 to be 296. My second volume is what I'm looking for. My second pressure is 1 atmosphere. And then for my T2, it'd be 0 plus 273, which is 273. So then I would solve for V. In this case, it would be just 1 divided by 273, so the reciprocal. So for my 273 So for my final volume, I would end up with a volume of 0.348 liters. Okay. Okay, let me see. Let me just do this one. So this question wants us to know if our canister will explode. It says at a pressure of 210 atmospheres, it'll explode. It wants to know if we have a volume of this many moles, this temperature, will we explode? So we're figuring out what the pressure is. So we're going to use ideal gas law, because anytime you have moles, you're probably going to use ideal gas law. And we're going to solve for pressure. So we have our volume in liters, we have our moles in moles. We don't have this temperature and the correct thing. So we're going to do pressure is equal to the volume, to the moles, 3.5 moles, times our constant. R, remember, always equals 0.0821. Liters times atmosphere over mole Kelvin. And then our temperature. Our temperature, we're going to have to convert it. Which is 1623 Kelvin. Over our volume, because we're solving for P. So when you do the calculation, we end up with a pressure of 233.2 atmospheres. So since it's greater than what it would be, is this going to blow? Yes, it is. Okay. Now, we have like 1 minute left in class. So what I'll do for the rest of it, these have to do with mass and how like we would use our ideal gas law to find the molar mass or the mass of the object or something like that. So I will do these in another video, and then I'll post it tomorrow. Okay, so tomorrow you guys will have problems like these, and I'll post a video on Google Classroom so that way you guys can work on them.